Welcome to Math with Professor V. This is video lecture for section 2.3 for Business Calculus on rational functions. This is just going to be a light covering of this topic for the purposes of a business calculus course. If you want a more in-depth video lecture that really delves into a thorough explanation of the properties of rational functions, I'll link the Precalculus video lecture in the description here. But if you're a business calculus student, you're not going to take the pure calculus series, this is going to be more than enough. So a rational function is defined by the following. We say f of x is equal to p of x over q of x, where p and q are polynomial functions and q of x is not zero. The denominator is not zero. So basically a rational function is a ratio or a fraction of two polynomials. And there's two important components for every rational function that we need to find when we graph them. That is their vertical asymptote, and then sometimes they have a horizontal asymptote. So if a function gets larger and larger in magnitude, meaning it could be positive or negative, it's just getting very, very large, without bound, as x approaches the number k, then x equals k is a vertical asymptote. And hopefully you've seen what a vertical asymptote looks like before, but if not, let me graph for you. Say k is right here. This is our vertical asymptote. I'm going to represent it with a dashed line. And if my function gets larger and larger as it approaches k, in this case it's going up to positive infinity, or maybe from the other side I'm going to draw it going down to negative infinity, then we say x equals k is a vertical asymptote. Okay, how do you find the vertical asymptote? Well, you find the zeros of the denominator of your rational function as long as it's completely simplified, when it's in reduced terms. So I'll explain that in a minute, but we will work on some examples. So just put this as a note to yourself. You're going to set the denominator equal to 0. That will give you the vertical asymptote or asymptotes of the graph as long as your rational function is completely reduced. Okay, then I said we may at times also have a horizontal asymptote. If the values of y, your function, f of x, approach some number k, as this is absolute value of x, meaning x could get big in the positive direction or x could get big in the negative direction. It just gets larger and larger. If the values of y level off or they approach some number k, then that line y equals k is a horizontal asymptote. So let's show what that would look like when you have a horizontal asymptote. So here's our function, rational function, and say I have a vertical asymptote, just for fun, I'll put one here. Okay, and then say we have a horizontal asymptote also here somewhere. And this is y equals k. Sometimes the graph will look something like this. It'll level off and approach k on this side, and then maybe over here, it's approaching k from the other side. Okay, so what is important to notice is the horizontal asymptote describes what we call the end behavior of the graph. So as you get really, really far along the x-axis, as x values get very, very large, the function levels off and it approaches the horizontal asymptote. And it approaches, same thing here, if x goes to negative infinity. Okay, now how do you find the horizontal asymptote? Well, you have to look at the rational function, and you have to look at the degree of the numerator and compare it with the degree of the denominator. And let me summarize for you basically how we're going to do that. I need a little space though, so how about I'm just going to add a little page in here. Okay, so we can do that. So let me just give you little notes to find the horizontal asymptote. Okay, so remember our function f of x is equal to p of x over q of x, right? So you're going to find the degree of p of x and the degree of q of x. I'll explain how to do that in a minute. If the degree of P of X is equal to the degree of Q of X, then you take the ratio of the leading coefficients, and then that ratio is whatever your horizontal asymptote is going to be once it's simplified. If the degree of Q of X is greater than the degree of P of X, so the degree in the denominator is higher, then your horizontal asymptote is automatically at y equals 0. It's just the x-axis. And then last option is if the degree of P of X, the numerator, is greater than the degree of Q of X, then that means there is no horizontal asymptote. Sometimes you'll have like an oblique or a slant asymptote, but that's beyond what we do in this course. Okay, so I'm just going to show you a couple baby examples so you guys can get an idea how to find the horizontal asymptote. Okay, so say we have, here's our function f of x, and it's 2x plus 4 over x minus 1. What's the degree of the numerator? Do you know how to find the degree? It's the highest power of x. So the degree of the numerator here is just 1 because we've got x to the first. Denominator also is degree 1. The degrees are equal. So we are in case 1 right here. The degrees are equal. The equation of my horizontal asymptote can be found by taking the ratio of the leading coefficients. What the heck? You look at the highest degree terms and you take the ratio of the coefficients. So you have 2 in front of an x in the numerator and 1 in front of x in the denominator. You just divide those. You take their ratio. So the horizontal asymptote would be at y equals 2 over 1, which is 2. Okay, not too bad. Let's change it up. G of x is 2x plus 4 over x squared minus 1. So what's the degree of the numerator? 1, very good. What's the degree of the denominator? 2. Since the denominator has a higher degree than the numerator, we're in this second case here. So automatically my horizontal asymptote is at y equals 0. Good, very good. I'm going to give you one more. H of x equals, let's do 3x squared plus, this is more spicy than what you're going to have to deal with, but just to show you, over 2x squared minus 4. Okay, what's the degree of the numerator? It's 2, right? And the degree of the denominator? 2. So they're equal. So my horizontal asymptote is going to be y equals the ratio of the leading coefficients of those terms. So it's going to be at y equals 3 over 2. Okay. So like I said, don't worry, you're not going to graph anything as spicy as example C here. I just wanted to make sure you got the idea of how to find the horizontal asymptote. And then let's just do one more for good measure. One more f of x. Let's do 3x squared plus 4x minus 1 over 2x plus 7. What's the degree of the numerator? Yes, it's degree 2. And the degree of the denominator is 1. So notice the degree of the numerator is higher than the degree of the denominator. That means there's no horizontal asymptote. Ooh, okay, good. So now you're ready for anything. If you need more examples though, you can check out the Precalc video lectures playlist, but I don't think you guys need to get too in depth, okay? Good, so let's practice graphing. The examples are not too wild, so we should be okay. First one, find any horizontal and vertical asymptotes and any holes. I'll tell you how to do that in a minute. That may exist for each rational function. Draw the graph of each function, including any x and y intercepts. Okay. Let's start off finding vertical and horizontal asymptotes. And I want to make sure first Is my function completely simplified? Yes, it is, right? I can't reduce it any further. And then let's write the domain. So remember, for a rational function, the denominator cannot be 0. So my domain is all x's such that x cannot equal -3. Very good. Okay, so first let's find horizontal asymptote. What's the degree of the numerator? It's 0, right? There's no x's, so the degree is 0. What's the degree of the denominator? It's 1, because we have x to the first. So degree in the denominator is higher than the degree in the numerator, then horizontal asymptote, automatically y equals 0. Good. Vertical asymptote. I'm going to set the denominator equal to 0, which we did earlier when we found the domain, and I get x equals -3. So that's my vertical asymptote. When you write the equation of an asymptote, it's the equation of a line, so you put equals. When you're writing the domain, you're saying x can't be that, so that's why we put not equals. The graph will never take on the value of x equaling -3. Okay, good. And then we're also asked to find any x and y intercepts. So remember, for x intercepts, you set y equal to 0. So for x intercepts, I'm going to set y equal to 0. And then already I can see we have problems. If I multiply both sides by x plus 3, I'm going to get 0 equals -1, right? Do you see that? Oh no, that's never going to happen. None. And then to get y-intercept, I'm going to substitute in 0 for x. So y equals -1 over 0 plus 3, so -1/3. Okay, that's good. So we have 0, -1/3 as our y-intercept. Okay, very nice. Let's put the asymptotes in and then figure out what the graph's going to look like. Now we have one vertical asymptote at x equals -3. So that means my graph is going to be cut up into 2 pieces since we have one vertical asymptote. And then horizontal asymptote is at y equals 0. That's the x-axis. I'm just going to add a little extra to the left and right of the x-axis so I remember that there's an asymptote there. And then I'm also going to plot 0, -1/3. Okay, good. Now, I told you there's 2 pieces to the graph, okay? And typically a rational function is going to have some sort of shape. Most of your options are something like this, or it could be something, in other quadrants, depending, different things happen, but basically that's the overall kind of curvature of it. And I know I'm going to have 2 pieces. Since this is my y-intercept, and I know there's no x-intercepts, the graph is never going to cross the x-axis. This graph is trapped underneath the x-axis here, and it's going to approach the horizontal asymptote. And then it's going to stay over here and get close to the vertical asymptote. So I already know over here it's coming down, down, down. And then over here it's never going to pop back up. It's just hanging out, getting closer and closer to y equals 0. Okay, that looks so good. Now for the other piece, because there's going to be 2 pieces. Either the graph is going to be up here or it's going to be down here. Those are my only 2 options. It's not going to cross. If it crossed, we would have gotten an x-intercept, and we didn't. But I don't know, is it up here or is it down here? So what we're going to do, let's pick a value for x and plug it in to the function to see should it be above or below the x-axis. So pick something on this side of the vertical asymptote. Pick something smaller than -3. How about -4? So y of -4, that's -1 over -4 plus 3. That's -1 divided by -1, which is 1. So the point -4, 1 is on the graph. Oh, then I know it's up here. And you just need that 1 point. So don't get carried away making like this huge table of values. It's not necessary. Okay, how was that one? Good. These are a little tricky to get used to, but just keep practicing. You got this. Okay, let's look at another example. Y equals x minus 4 over x plus 1. This rational function, it's completely simplified. Let's write the domain though. The domain is all x's such that x cannot equal -1. Very good. So let's find the asymptotes. Vertical asymptote I get by setting the denominator equal to 0. So it's at x equals -1. Now let's look at the horizontal asymptote. How do we find that? What's the degree of the numerator? 1. What's the degree of the denominator? 1. So the horizontal asymptote is going to be equal to y equals, you divide their coefficients, so 1 divided by 1 is just 1. Okay, that was pretty straightforward. We doing okay? Now let's find x-intercept and y-intercept. So x-intercept, we're going to set y equal to 0. So we have 0 equals x minus 4 over x plus 1. Multiply both sides by x plus 1. And you get 0 equals x minus 4. Can I tell you a little shortcut? When you're finding x-intercepts for a rational function like this, all you need to do is check where the numerator is 0. Because when you set the whole rational function equal to 0, the first step that you always take is you multiply by the denominator to clear it out. And you'll always have 0 times the denominator, which gives you back 0. And you end up with 0 equals the numerator. So you can totally skip to this step when you're finding x-intercepts. Just set the numerator to 0. Okay? So x is equal to 4. And I'm going to write that as 4, 0. That's a point, the x-intercept. That's important. Don't leave it x equals 4, you guys, because the vertical asymptotes equation is x equals something. You're going to get confused. Was this the asymptote or was this the intercept? So I don't want you making a boo-boo. Write it as an ordered pair, then you'll stop yourself from getting them mixed up, okay? Y-intercept, this we just plug in 0 for x. So y equals 0 minus 4 over 0 plus 1. That's -4. Again, write that as a point in ordered pairs, 0, -4. So let's fill everything in. We have x equals -1. That's my vertical asymptote. Y equals +1 is my horizontal asymptote. And then x-intercept is at 4, 0, 1, 2, 3, 4. Y-intercept 0, -4, 1, 2, 3, 4. You know, I didn't label my axes. X, Y, please forgive me. Okay, again, this graph is going to have 2 pieces. I can already tell this piece is going to go like so. Yes. So let me connect everything. This one's actually going to be easier than the last problem. You'll see why in just a second. Now, for the other piece, is it going to be up here or is it going to be down below the horizontal asymptote? I don't need to test a point this time. I know for sure. Why do I say that? It can't be down here, because if it was down here, we would have another x-intercept somewhere, and I found the one and only x-intercept at 4, 0. So that means it has to be up above the horizontal asymptote here. Okay, so just follow that shape. Make sure you put arrows and kind of hug the asymptotes. Don't float far away from them. The graph approaches those asymptotes. And that's that. Beautiful. Okay, now, last one, I'm going to show you what it looks like when you have a hole in your graph and how to deal with that, okay? So here we have y equals 9 minus 6x plus x squared over 3 minus x. First thing, so looking at this function, let's rewrite it. Let me put the numerator in descending powers. So let's put x squared first. Then we have -6x and then +9 over 3 minus x. So let's write the domain. Remember, we don't want the denominator to be 0. So the domain is going to be all x's such that x cannot equal 3. Good. But in the beginning of the video, when I gave you the rule to find vertical asymptotes, I said you set the denominator to 0 only after your function's completely reduced or completely simplified. And this one isn't. I can actually factor and simplify. Can you see how to factor the numerator? X squared minus 6x plus 9. It's x minus 3 times x minus 3. And then in the denominator, we have 3 minus x, which actually I can cancel with one of the x minus 3's. And you might be thinking, Professor V, I think you've gone crazy. They're not matchy-matchy. How can you cancel? I want you to make a note, okay? A minus B divided by B minus A is equal to -1. Why? Okay, let's check. Don't just believe what people tell you. You got to verify. Say I take this rule I just gave you, this little fun fact, okay? And we multiply through both sides by B minus A. Okay, so this is gone. This is gone. And then I have A minus B equals, distribute that negative B plus A. Well, isn't that the same as A minus B? Okay, so just as a fact, A minus B is equal to negative B minus A, which is the same as saying A minus B over B minus A is -1. Well, why is this helpful? Because what we can do is we can actually cancel out x minus 3 and 3 minus x, but remember that gives us -1, so just add a minus sign in front of your function. Okay, let me get this out of the way so I can just keep simplifying over here. There's the note. Good. Okay, so then now I can say y equals -x minus 3, which is -x plus 3. That's a line, right? This is a line. So we have no horizontal asymptote, no vertical asymptote, but we do have a hole. We have a hole at x equals 3. Why do I say that? Because originally, right, before we canceled out that 3 minus x, we wrote the domain and we said x can't be 3 because of how the function was originally given to us. Now that we've simplified, we don't see that original problem, but it still is there. It's just hidden once we've simplified. So 3 minus x is not so dangerous anymore that it's going to be a vertical asymptote. When you have a factor cancel like that from the numerator and denominator, I think of it like it got downgraded. It's just going to be a hole in the graph, not an actual asymptote. So the hole is going to be at x equals 3, And then how do I get the y coordinate? You just come and plug in 3 for x into the simplified or the reduced equation. So the hole is going to be at 3 comma -3 plus 3 is 0. So the hole is at 3 comma 0. Okay, and you're just going to graph a line. So the hole is at 3 comma 0. You graph that with an open circle. And then can you plot -x plus 3? Y-intercept is +3. Here's my x-axis, here's my y-axis. That's enough, right? I've got 2 points. The hole you can use as, a way to guide the line. There's the slope, bada bing, bada boom. How we doing? Okay, very good. Now, the reason we just did this little brief recap of rational functions is because in this course, we're going to study average cost. And if you look at the formula for average cost, it is a rational function. Yes. Okay, so we looked in the previous lesson at the cost function. And cost function has the form c of x equals mx plus b. Hopefully you remember, where x is the number of items produced, m was the marginal cost per item, conveniently m marginal cost, m slope, I love it. B is the fixed cost, and we have our cost function. Now we're looking at a new function, average cost per item, and it's given by the following. So average cost we represent by C bar of X. Okay, if you've taken a little bit of statistics, then you know when we write the mean, the notation for the sample mean, we use X bar. So hopefully saying a bar reminds you of average. And the way we find C bar of X is we take our cost function and we divide by X, the number of items produced. That should make sense. You take the cost divided by how many items, that gives you the average cost per item. So it's MX plus B divided by X. Great. So let's work with this average cost function now. Can you see how it's a rational function? X in the top, X in the bottom. Suppose that the fixed cost to make coffee mugs is $200. And the marginal cost to make one mug is 85 cents. So write a formula for the average cost function. First, let's write a function for C of X. So C of X is going to be marginal cost, 0.85 times X, plus fixed cost 200. So average cost, C bar of X, you take your cost function and you divide by X. And then let's simplify. Well, we'll simplify later. Let's just leave it. We like this. Let's just box it up and say, you know what, we did what you wanted from us. Okay. Next question, part B. As the number of mugs produced gets increasingly large, what does the average cost per mug approach? So we haven't officially learned limits yet. I'm just going to answer this question intuitively with you guys, okay? So now let's simplify our cost function. I'm going to split each of the terms in the numerator over the denominator separately. So I'm going to write 0.85x over x plus 200 over x. And then hopefully you can see this gives us, these x's cancel, right? So it's just 0.85 plus 200 over x. And it's asking me right now, as the number of mugs as x gets large, what does average cost C bar of x approach? So as x gets very, very large, let's see what's happening. 0.85 will not change. That's a constant. This denominator is getting bigger, bigger, bigger. Think, what happens when you divide by something getting bigger, bigger, bigger? 200 divided by 10 compared to 200 divided by 1,000 compared to 200 divided by 1,000,000, 200 divided by 1,000,000,000. Can you see what's happening? 200 divided by x will approach 0. It'll get tiny, 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 tiny and become insignificant. So that means the average cost is going to approach just the 85 cents because that's not changing as x changes. So the average cost approaches 85 cents. Okay? Which is good news if you're looking from like a manufacturer's perspective, right? So those fixed costs, that $200 that you spend up front might be significant, but if X gets increasingly large, then that $200 doesn't become such a big deal. Okay, last idea, they want us to sketch a graph of the average cost function. So let's figure out where the asymptotes are, and then maybe we'll make a little table plot some points. So my average cost function, before I simplified it, it was 0.85x plus 200 over x. So let's find the asymptotes. Vertical asymptote, where the denominator would be 0, that's just at x equals 0. So that's the y-axis. So this is our vertical asymptote. Horizontal asymptote, degree of numerator and denominator are the same. So I'm just going to take 0.85 divided by 1. So it's at y equals 0.85. Okay, that's going to be a little rough to graph. So let's make a table 2. This is x. This is going to be C bar of x. We're graphing average cost. And let's just pick some values for x and compute what the average cost is for each of them. Okay, just so we have a little more to go off of. And we're not going to draw the full rational function like we did in the other problems because this is an application. It doesn't make sense, you know, for x to be negative, for the cost to be negative. We're just going to stay in this first quadrant here. Let me pick different values of x, though, to get things started. We could do 1, 2, 3, 4, then maybe we'll jump to 10, okay? So you can just punch everything in your calculator. This first one we can do in our head, though. If x is 1, average cost is $200, 85 cents. If x is 2, let's double check, plus 200 divided by 2, average cost is, yes, $100.85. If x is 3, 0.85 times 3 plus 200 divided by 3, average cost is 67.52. If x is 4, 0.85 times 4 plus 200 divided by 4, 50.85. And then if x is 10, 0.85 times 10 plus 200 divided by 10, 20.85. So let's plot that. So average cost needs to go all the way up to 200. So let me scale by 20s. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. And then x will go up to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So let's just start filling everything in. We have here, if x is 1, the cost is 200.85. So just go a wee bit higher than 200. 2 is going to be 100.85. 367.52. 4 is 50.85. Remember, each of the vertical tick marks is 20. And then 10 is 20.85. I'm not going to put an arrow here because we're not going to make less than one item unless like we shut the factory down, you know. So just end point there. Ooh, it's looking so nice. And then you can continue, draw an arrow. It's going to go down, down, down. You know, it shouldn't have that wiggle there. Excuse me. It's just approaching 0.85, which is kind of hard to show. So just do a little dash mark there. Very good. Okay, so that concludes the lesson. You really don't need to do too advanced computations with rational functions in this course. As long as you know how to find horizontal, vertical asymptote for problems like this, you'll be in good shape. So that concludes the video. Give it a thumbs up. Subscribe if you haven't already, and then stay tuned. I'll have more business calculus video lectures coming your way. If you're in regular calculus though, then just hop over to the Calculus 1 video lectures playlist or Calculus 2 video lectures playlist. I have more content there. And you can also follow me on Instagram, TikTok, Twitter, Math with Professor V. I love you guys so much. I'll be back sooner than later. Bye.